We're interested in looking at probability distributions. Basically, what is a probability distribution? It assigns a value every outcome in a sample space. Now, outcomes could be numeric, so elements of the sample space are numeric. An example there would be simply the roll of a die. I could get a 1, a 2, or 3, so the results are numeric. But they could also be categorical, and that's where the sample space are just names, like blood types. We have, well, what are they? You have A and O and all those sorts of things. Random variables then. A random variable is a function, and the value of that function turns out to be a number, and that number is determined by the probability of the event happening. Notation. So when we're playing with this idea, the random variables we use an uppercase letter for. The actual value we would express with a lowercase letter, so the equivalent lowercase letter. And random variables can be continuous, and it's continuous if all the possible outcomes form like an interval. There are no gaps in it, if you like, a nice clean interval. Whereas they can be discrete if it's countable. So lots of just individual scores. There's lots of gaps in there. Just because it's countable doesn't mean you can't have an infinite number of them. And here's an example one here. I was interested in looking at the number of times we roll a dice before we get a 6. Well, there's an infinite number of possibilities, because theoretically you might never roll a 6. You could just keep rolling and rolling and rolling and rolling. It's still discrete, but we just have an infinite number of possibilities. So here's a simple little example. A coin's going to be tossed 3 times. The random variable x is going to be defined as the number of heads thrown. That's what we're interested in looking at. My sample space, these are all the possible outcomes, and I've got them arranged in order there. So head, 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 tail, head, and so on. They're all the possible ones. That's the sample space. But the sample space of the random variable, when I now convert that to a number, would be 3, 2, 2, 2, 1, 1, 1, and 0. Because we're interested in looking at the number of heads thrown. So for head, 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 3. Head, head, tail, 2. And I could put that in a table. That's our probability distribution table. And so here's where the lowercase and uppercase comes into play. We're saying the probability that my random variable is equal to a particular probability. So small x is the actual value. And probability of getting no heads was 1 out of 8, and then 3 out of 8 for ones, and so on. And that would be the graph of the probability distribution. A very boring graph for this one, but that would be the graph. Some properties then of this function, probability of x equals x. What do we know? Well, we know it's got to be a positive number, because we're talking about the probability of something. We don't get negative probabilities. And we also know that all those probabilities should add up to be 1. Because if we've got every possible outcome, then it covers all the possibilities, therefore they add up to be 1. If it turns out that those probabilities were the same for every single event, then we just say it's a uniform distribution. Everything's the same. Everything's equally likely. And that will do us to start off with.